is the universe made of? Scientists have determined that normal matter, the stuff that makes up the Earth, the stars, and everything we can see, only makes up a small portion of the universe. The rest is made up of two mysterious components that are shaping our universe in profound ways. Much of the mass of the universe is made up of something called dark matter, which neither reflects nor emits light, but like the matter we can see, pulls things together with gravity. And space itself seems to be permeated by an unusual force called dark energy, which is driving things apart.
But the interesting thing is we don't know yet what dark matter is. That is to say, we know ordinary matter is composed of fundamental particles like quarks, electrons, but we don't know what the dark matter is made of.
We're made of atoms. Atoms are the only things we knew of until about 30 or so years ago. They're just a small part of the story. The two big actors in the story are dark matter and dark energy.
Based on current estimates, scientists believe that only 5% of the universe is made up of normal matter, 27% is made up of dark matter, and a whopping 68% is made up of dark energy. So what are they? And how do we know they exist? Although we can't see dark matter, we can tell it is out there from the effect it has on regular matter, such as galaxies and stars.
Dark matter is matter which we infer to exist because we see its gravitational effect. And in particular, one example is that if you look at the rotation of galaxies, and this is how the discovery was really first made, it turns out the galaxies are rotating much faster than they ought to be. Rotating at that speed, they should just fly apart if the only thing that was holding them together was the gravity from the matter that we see. So the inference is that there must be more matter there, and that's what we call dark matter.
We can track where dark matter is located through an effect called gravitational lensing. According to general relativity, massive bodies bend the fabric of space-time, and that means they bend the paths of light. Astronomers can see this light bending in places where there are no visible chunks of matter, such as stars. It must be caused by dark matter. Through these observations, scientists have found a cosmic web of dark matter, vast lumps and long threads of it. It is spread throughout the universe, but tends to be concentrated in halos around galaxies. Indeed, it is considered to have been integral to the formation of the large-scale structure of the universe.
In our universe, not in ordinary life, but in our universe, gravity really is the most important force. And for the first 10 billion years, gravity was the master builder. And so it was the gravity of dark matter that pulled together matter into galaxies and clusters of galaxies and eventually into stars and solar systems like our own.
So what is dark matter made of? No one knows for sure yet, but there are a number of theories.
And so one of the big questions about dark matter is, well, first off, what is it? And then secondly, how, if at all, does it interact with normal matter?
It doesn't give off light. And so that must mean that it's not made of atoms, because atoms give off light if you kick them or tickle them or do something to them. And so this dark matter must not be made of charged particles. And we're now to the point that we believe that it's a new form of matter. Particles left over from the Big Bang. It's a new form of stable matter that we've yet to identify.
There are a number of different experiments focused on finding dark matter, trying to catch it as it occasionally bumps into normal matter, but none of them has been successful so far. Dark matter particles might just be created in earthly laboratories too. At the Large Hadron Collider in Switzerland, where particles smash together near the speed of light, there is some chance that dark matter particles will pop out. And astronomers using some of the world's largest telescopes are observing the cosmos with ever more precision to learn about where dark matter is located. It was through their efforts in the late 1990s that scientists learned about the other mysterious force that is shaping our cosmos, dark energy. Astronomers studying distant supernovae discovered it accidentally by observing that the expansion of the universe seemed to be speeding up. Michael Turner coined the term dark energy to describe the mysterious force that seemed to be pushing the universe apart.
This could be the most profound mystery in all of science. The fact that the universe is speeding up. Hidden in Einstein's theory of general relativity is the possibility for very weird stuff, which we now call dark energy, to have gravity that instead of pulling things together, pushes things apart.
The idea that the universe could expand or contract showed up in early drafts of Albert Einstein's theory of relativity, but Einstein himself believed the universe was of a fixed size. To get things to add up correctly, he fudged his equations by inserting a fixed value he called a cosmological constant. Only later, when it was shown the universe was in fact expanding, did it become apparent that his equations were right to begin with. Einstein's cosmological constant might also end up accounting for dark energy. No one knows what dark energy is exactly, although many theories have been postulated.
We know a lot about what dark energy isn't. So it's not particles. We can't break it down into individual particles. It's more like a medium or a substance. Unlike dark matter, dark energy doesn't clump up. It's uniformly distributed.
One suggestion is that it is energy folded into the fabric of space itself.
Most likely is that it's simply vacuum energy, the energy of empty space. The vacuum is not a simple state at all. It's a very, very complicated state. In the vacuum, particle and antiparticle pairs are constantly appearing and disappearing, and we also think there's at least one field, what we call the Higgs field, which has a non-zero value everywhere in space.
So dark energy is, it's actually not associated with matter. I mean, one of the amazing things Einstein taught us was that the absolute value of energy is meaningful because there's gravity associated with it. So even if there's no actual particles around, the universe itself can carry energy. In fact, that's expected.
As space expands, so does the amount of dark energy, so there will be more of it to push the universe apart. What astronomers don't know yet is if the rate of acceleration of the expansion will change over time. If it does, that could have profound implications.
Is the acceleration itself accelerating? If it is, then dark energy will rip apart the universe. It'll rip apart clusters of galaxies and then solar systems, and then planets, and then eventually us.
But the dominance of dark matter and dark energy have shifted over the lifespan of the universe, with dark matter playing a stronger role in the early years and dark energy gaining traction more recently. What will happen to our universe depends on the interplay between these two dark titans. If dark energy becomes more dominant, the universe may thin itself out of existence in what's called the Big Rip. But if dark matter's influence should increase, that could collapse the universe back upon itself in a big crunch. And if neither force changes dramatically, space may just continue expanding outward indefinitely. For cosmologists trying to foresee the ultimate fate of the universe, much remains in the dark.